In this last video associated with organometallics, we're just going to do a few problems and look at a couple of feature things about organometallics that probably are not going to appear on the exam, but it's good to just know what is currently going on in chemistry. Okay, so the first problem we have here is something called a roadmap problem. This is where you transform a simple material into a complex material, and you have to provide the structures of the little interesting things that are going along, that are being produced along the way. All right, so let's look at this one. And the beauty of a roadmap problem is that you can work forwards or backwards. If you find the early stuff to be difficult, you can concentrate on the late stuff. And I'll just give a demonstration of that. Because this is a slideshow, I've got them in order, but I'll just say something about going in reverse here in a second. Okay? All right, so our first reaction there, we're taking a halide, treating it with magnesium and ether, and of course that is making a Grignard reagent, and that's compound A. Let's say we totally forgot that reaction. We're not totally messed up because we can probably remember that in this last reaction, we're looking at carbene addition. Okay, all right, and we know that that reagent there, KOH bromoform, is the reagent for making a dibromocyclopropane from an alkene. So E would have to be, okay, I don't know why this computer is having this delay factor here, but we'll still make nice, neat structures. All right, so that would have to be the structure of E if you got stuck and you couldn't figure out A. So you can start at two different ends. All right, we're going to treat it with formaldehyde, and that's going to make the primary alcohol with one more carbon in it. We're now going to treat this with PBr3. This is not a Chem 314 reaction. It's from the first half of the class, but remember PBr3, you're going to see that used a lot in this class because there's a requirement for halides in a lot of the reactions. All right, so we need to turn the alcohol into the corresponding bromide with PBr3, and there's compound C right there. Okay, we could not use HBr, right, because that would it's primary and wouldn't be in high yield, and it's might rearrange to give us the tertiary bromide if we did. So PBr3 is the ideal reagent. All right, here we're going to show the Grignard addition, but we're going to show it a little differently because we're going to do it in series. We're not going to do it one step at a time like we did at the top. Okay, so in step one, we're turning the bromide into the Grignard reagent. In step two, we are adding the aldehyde. Okay, so when you react a Grignard reagent with an aldehyde, the product is a secondary alcohol, and that right there is our product. Okay. All right, we're now going to treat this with sulfuric acid and heat. And this, again, is an older reaction. This is acid-catalyzed dehydration. All right, we're going to remove water from an alcohol to make an alkene. All right, so it's going to just make what E is. We already identified E by working backwards, but we can see how it we also arrive at the same compound by working forwards. All right, I want to illustrate another thing with these roadmap problems. I always have been saying that we work this up with H3O+, but it really doesn't require very strong acid. In fact, it doesn't really require acid at all. Just plain old water will do this. I've put H3O+ to conform with the book, but this H3O+ we're using to quench Grignard reactions is very weak. We really need a much stronger acid to cause the dehydration to occur. So this mild acid we're using to quench the Grignard reaction is unlikely to cause the dehydration. Okay, this is a forward synthesis. How do we convert A into B? And we're going to grab our extra carbons from compounds C and D. Okay, we also have another hint. Use the ring closing metathesis as the very last step of the reaction. All right, so recall that in the ring closing metathesis, we will be making our alkene from the precursor that has a couple of extra carbons in it, right? All right, so our precursor compound for the very last step is that. All right, right away, you can see the allyl group right there. All right, so the way to look at this is that we're going to make that CC bond there that I've shown with the slash mark from compound D. Okay. All right, so this is an alcohol with an allyl group attached to the alcohol carbon. So an ideal way to do this, if we have the bromide, is to convert the bromide into the Grignard and then add it to the corresponding ketone. All right, so there is this process. We're going to take allyl bromide, convert it to the Grignard reagent, and add it to the ketone that you see right above it. All right, what you'll notice here is that this looks like A, except it has this extra bond. And what we need to do now is introduce that whole group there, which you see corresponds to everything in C that isn't chlorine. Okay. All right. Note that this ring is very electron rich. And this is going to be used to do the Friedel-Crafts acylation reaction. Okay, so this should ideally be set up to do that very nicely, right? All right, so if we took compound A, compound C, and some aluminum chloride, we would expect to produce the compound that you see here. Both of these are activating in the ortho and para positions, and since the position that I've indicated there away from the methoxys is a little bit less hindered than right beside the methoxys, we're more than likely going to get it to go there. Recognize that if you look at what's ortho-para to methoxy, it doesn't help you. Everything's ortho-para to methoxy. All right, so we're just going to add it to the sterically less hindered position. Okay, all right, so there's that one. All right, this is a reaction that's kind of a feature at the end of the chapter book, the end of the organometallic chapter, but this is a very important reaction. In fact, this reaction here is actually much better than the copper catalyzed reaction that we looked at earlier for making CC bonds. This won the Nobel Prize in 2010 to Suzuki at Hokkaido University, Nagishi at Purdue, and Heck at the University of Delaware. And what they found is that you can do what looks like an illegal SN2 reaction just by adding a little bit of a palladium salt to the reaction mixture. The mechanism is a little bit more complex. I'm not going to go through the mechanism for this process because it deals deeply with the fundamentals of organometallic chemistry. It's unlikely that I would put this on the exam, but it's very likely that organic chemistry classes 5 years from now are going to be learning this reaction instead of the copper catalyzed CC coupling. Okay, so this one here with a boron as our organometallic is known as the Suzuki coupling. Okay. And this one here is known as the Heck reaction. Okay. And we're basically, in this case, adding the aromatic ring to the double bond and then eliminating something to get the double bond back. Again, I'm not going to go through the mechanism for this, but these are perhaps the most important way that people couple carbons together nowadays. Okay, let's look at some other organometallic systems. This is a result that befuddled a lot of people back in the 1940s. If you take cyclopentadienyl lithium and iron dichloride, you get this compound, but it turns out that what you get is a very stable compound. And if you look at this structure, it's not expected to be stable. This compound, what you get from this is stable to air and water. It's has a very rock-like consistency. Okay, and so the structure that was proposed instead of that one is this one, which is known as a sandwich compound, where the metal is bound to the whole delocalized aromatic system of the cyclopentadienyl ring. Okay, and ferrocene is the structure we're looking at. Ferrocene, its reactivity very much resembles benzene. Okay, so you can do electrophilic aromatic substitution on ferrocene just as you can on benzene. And in fact, in undergraduate labs, ferrocene is actually preferred because it's not volatile and not nearly as toxic as benzene. Okay, all right. Here's another important one. This came along after ferrocene, and let's see, this did win the Nobel Prize also to E.O. Fisher in I think 1967, something like that. Actually 1976. A little later. Yeah, got it backwards there. All right. This catalyst here with two cyclopentadienyls flanking a zirconium, it's kind of like ferrocene, except it's got zirconium and a couple of extra chlorines, and this is known as a Ziegler nanocatalyst. And this is a revolutionized polymer chemistry. Okay, so it activates by taking this is called zirconocene dichloride and diethyl aluminum chloride, and from this you get a catalyst known as a Ziegler nanocatalyst. It's a little bit ill-defined, but it is a kind of an amorphous gray powder that works miracles. One of the things it can do is it can polymerize propylene in such a way that we get a stereoregular polymer. And this improves the crystallinity properties of polypropylene. If you don't control the stereochemistry, it has the consistency of chewing gum, but it's a lot firmer when you do it this way. And this is how let's see, I believe the Stainmaster carpet is polypropylene, and you can look at the structure and appreciate why something would be stain resistant. What is going to be attracted to something like that? It's going to um, the only intermolecular forces available to it would be van der Waals forces, right? Okay, so these are some very important organometallics. Let's see, without humans doing chemistry, none of these organometallic compounds we've talked to date would even exist. But there is one naturally occurring organometallic compound. That's vitamin B12. Okay, and this has a bond between cobalt and a cyanide group, and related to that is coenzyme B12 that actually has a covalent bond between the CH2 group here and the cobalt. There's a very long bond right there. Okay, so this is an important vitamin. I think, what is it, prevents rickets or something like that if you have a B12 deficiency. Let's see. This is what, when you take a multivitamin and have fluorescent yellow piss the next morning, this is the compound that's responsible for that. So, yeah, it's important. I guess that's not really all that important of a thing to know, but just thought I'd throw that out there. Okay, all right. This is research from my own lab. I just thought I'd just throw this out there. This would not be on the exam, but you can see that this has an organometallic system, a carbon-chromium double bond known as a carbene complex. All right, and this is a reaction we invented where these 5 carbons here are going to incorporate themselves into the new structure, and we use this as a key step for the synthesis of the experimental anti-cancer drug antiphene. So this actually prepares this compound quite quickly from relatively simple precursor compounds. Let me just tell you about a reaction in the synthesis here that's kind of might pique your interest. Okay, so when we do the first step of the reaction, this comes out as 2 CH2 groups. Okay, all right, so we treat this now with palladium on carbon, which you recognize as a hydrogenation catalyst, but we add no hydrogen. So since there's no hydrogen, it does a dehydrogenation. Okay, and the reason it does the dehydrogenation, you can probably figure it out, is because it makes that third ring completely aromatic, right? So there's a lot of thermodynamic driving force for ripping 2 hydrogens out of that molecule. So sometimes the hydrogenation reaction can be reversible in special cases, and this is one of them. Okay, I think this is where this chapter ends. So this will be the last video for organometallic chemistry. However, all these reactions that we talked about, particularly the ones with lithium and magnesium, we're going to be revisiting for the next few chapters. And then in chapter 20, we're going to revisit the copper chemistry, because we're going to see that there's another reaction that these organocopper things do that's extremely useful. Okay, so this is going to end now.